All right. So what I wanted to do is that I believe I gave you a problem like this in one of the quizzes. Can you hear me?
Yes.
Oh, yeah. Do you remember what was the that I gave you this problem? Was one quiz or exercise? What was it?
I think you just gave it to us for notes, not like as an actual problem.
Ah, okay. So what I decided is to create a problem out of it. And so here we give this parallel plate capacitor, 10 volts, 0 volts in the lower. And each one of them has a metallic plate on top and then a metallic slab in between. So it's a piece of metal, perfect conductor. And so it says like the conductors behave as if they had infinite width and length, and assume that the outer conductors behave as if they were of infinite thickness. So practically, and then it says to find the capacitance A, capacitance B. Now, in this particular case, what I would say is exactly so if I were to ask you about a problem like this, then practically what you need to remember is on how the charges will distribute. And so, for example, if the charges start with a positive voltage at 10 volts, the upper plate, so will be all positive charges there, uniformly distributed. And then because of that, you're going to have all of the negative charges in the metal slab to be aligned across the positive from the top, and then all of the positive from the metal slab be aligned along in a way so that they align across the negative in the lower metal. So practically here you have two capacitors in series, all right? Even if it's not a dielectric, what you have in between, but it's metal. And so you find the capacitance of one, which is given by this, epsilon naught since in free space, area divided by the separation, H1. The second one is given by this, epsilon naught, the area divided by separation H3, H1 and H3 are the same. This is what you get from epsilon naught. And if you plug in there, and then you pay attention also to the units, all right, remember that epsilon naught is always in farads per meter. And area is going to be millimeter square from here. And the thickness is going to be in millimeters. So practically from there, and then if you convert the millimeters in the meter, rather in 10 to the third millimeters, and you plug in, you find that CAB and CBC are equal to 1.77 picofarads, and because you consider them in series, so the total capacitance is going to be half of it. So that's how I would solve this problem. All right, so for example, and then let me just give you this. So in this particular case, we connect the two metals. Okay, and then if you connect the two metals on top, so practically all of the positive charges and the negative here will cancel out. So it's going to be zero field here. There is not going to be any field in this area. Oh, let me in fact make sure it's recording. Okay, zero field here. And as a result, the only capacitor is going to be the CBC capacitor. because the CAB has been shorted. So I would say the total one, in fact, I have to remove this. And to be accurate, I have to put AC. It's going to be this one. Okay, do you see that? That's for a solution. Any variations of this? Let's see what I could give you as another possibility.
Dr. Katahi, could I just ask you a quick question?
Of course.
So in that first case where A and B are not connected, the only place the electric field is where the metal slab is not located. And then when you're connecting A and B or B and C, the electric field is only present in the spots where they're not connected.
Yes.
Okay.
Yeah. So one other problem I could give you is the following. Let's assume that now you have some new problem. What did I say here is problem one? Problem one. And so here will be problem two. So the I can give you different ones, but let's stay with the same, the parallel plate capacitor. So we have one plate here. Anyway, I try to make it thick. Cut. All right, this one. And then another plate here. So I could build on the previous problem and say, I have this slab here. All right. But now I have a dielectric here too. Or I could do the following. I could, so if I were to have this to be a metal, let me see, use this one for metal here. And then what I could have in addition to that is a dielectric underneath it. All right, so that could be a dielectric. And then could be air here. So for example, I could give this to be H1, H1, here, H2, H3, and H4. And as I said, this one got it out. Okay, let me use it. So this one. All right, so this is metal, and the same thing. I put here a voltage V, then I put here, so practically I connect that to a VD, that is 10, and then I connect this to the ground. And then the first thing, one, is to ask for the total capacitance. And how would we find here the total capacitance? So we'll do the same thing as before, all right? So we'll say the total capacitance is going to be made out of 4 capacitances. 1, Well, the metal is, there is no capacitance there, so it's 0, because the field is 0 here. And then, so practically for H2 we'll have 0, then H3 is another one. And then for this part H4 is another one, where C1, so 1 over C total is going to be 1 over C1 plus 1 over C3 plus 1 over C4, where C1 is going to be epsilon naught A, say the area is A, divided by H1. C2 is 0, we said. C3 is epsilon R epsilon naught A over H3, and C4 is epsilon naught A over H4. And then if you have the values, so practically it's going to be 1 over C total is 1 over epsilon naught A. And then here you will have H1 plus H2 divided by epsilon R plus H4, H3 rather, for this one. So that's what we have. And so from this you find the total. I could, yes, any questions on this one?
Yes, I'm sorry, Professor. How do you know like there's a capacitor like 1, 3, and 4 is like how it's connected? I'm kind of just a little lost on that.
How they are connected in series?
Like, how do you know it's like there's a C? How do you know like C2 is 0 and like there's only
Because
gonna
the
be...
electric field is 0. There is no electric field there.
Okay, so that's a given part of the problem.
But this is metal, is a metal. It's a conductor, and the conductivity goes to infinity, which means we said in perfect conductors, there is no electric field inside the conductor.
Yes, thank you.
You're welcome. Okay. Another version of this, it could be to give you, let me think. Half of a dielectric in there, or give you two separate dielectrics, all right? So you remember how to do something like that. Have a metal in here, could have a metal, and then you have two separate dielectrics there. How would you do this? Do you know? Who will tell me?
I think you first have to do the bottom two in parallel, and then
yes,
you computed that you do with
yeah. So practically the equivalent, and then let me just put it here because I need to make sure that it's consistent with. So this is metal. All right, so, and then of course, if I do that, not only you will know A, which is the area, you will have to put here this, VD, you will have to know that. You will have not only to know A, but you have to know A1, which is the area that goes over here, and A2, which is the area that goes over here, and then epsilon 1 here, epsilon 2, H, H1 here, H, say 3 here, and H4. And the equivalent to this circuit is going to be the capacitor here plus, there is 0 for the metal, then these two. All right, where C1, C, say 2, C3, where C1 is going to be epsilon naught A over H1, C2 will be epsilon 1 A1 over H3, C3 will be epsilon 2 A2 over H3, and we have C4, I forgot that. And then we have C4. Okay, so it's C4 is epsilon naught A over H4. Do you see how I did this? Do you understand that?
Yeah, so it's C1 and C4 pretty much air.
Yes.
Okay.
Yeah.
It's also so the gray part, that's again the conductor, and because it's a conductor.
Yes, there is no
Okay.
field and there is no capacitance, therefore.
Okay.
Why there is no capacitance?
Because there's no field, so I think that would mean that there couldn't be a charge there, and
Yeah, there is nothing, there is no activity, all right? So there is no capacitance, there is no capability of storing anything there in a metal. If there is conductors and there, that's it. You know, it's everything in one potential. So practically, so the voltage across a metal, because it's all at the same potential, how much is the voltage across any 2 points of a metal? So, which is exactly this. All right, so there is nothing, no charges in there to create any activity. That's why. Okay, let's try to solve another problem that I have. Okay, this is a little longer. In this problem is more out of the statics. Okay, and what I have here is so it's a structure, and I will describe it. The green area is a metal which is thick, but the charge is distributed evenly throughout the conducting cylinder. So it's conducting, but it's not a perfect conductor. So the charges distribute throughout. All right, so I gave it to you as it's a given. It's not why and how, I just gave it to you. And then, so I have here the inner radius of this conductor, the green one, where all of the charges distribute evenly. And then I have the thickness of the conductor. And I also have the charge density, volume density, as you can see here. So in fact, this one. And then outside of this, I have a dielectric. And the dielectric, it's a dielectric there that with epsilon, which I give here. All right, and epsilon sub r equals 4. And then I give you A, which is the radius, the internal radius of the inner conductor, I give you B, which is the internal radius of the outer conductor. I give you T2, which really, in this particular case, is the outer conductor and is grounded. Okay, and then what I'm asking is, I would like to find the electric field between these two conductors. So practically, I would like to find the electric field from 0, from the center, I would say. In this case, I could ask to find the field from the center, which is O, all the way to the outer conductor, which is here somewhere. All right. And I would like also to find the capacitance and so on and so forth. So the most critical thing in a problem like this is to find the field. You cannot find a capacitor without finding the field. Why do we need to find the field? What do we use the field for?
So you can calculate electric potential.
Yes, exactly. We calculate the electric potential and then we find the voltage difference between the potentials on the two capacitors, on the two metals, excuse me, two conductors. And then from this V, we have take Q divided by V, and that gives us capacitance, all right? So always we need to find the electric field. From that electric field, we can find the potential and therefore the voltage difference between the conductors. And then from that, we find the capacitance. So we start with the field always. Now here, I took the inside of the conductor first. So I took practically this area that you see me circling. I took this area and I expanded it here. So there is an inner side of this area, which is region 1. There is the area where in the conductor, the inner conductor, where all of the charge distributes, which I call area 2 here. And then there is the outside area, which is called area 3. Now, what I know, first of all, you need to remember that because this problem has a cylindrical symmetry, and it's an infinite cylindrical structure, infinite long, but I consider, a given length for that, L, for example. It has total symmetry though, cylindrically speaking. So I can use Gauss's law if I have that kind of cylindrical symmetry. I do not need to use Coulomb's law, which is more complex. I use Gauss's law. Do you understand that, why I'm doing it?
How'd you go from this picture to the earlier one? I don't think I got that.
So have you thought about when do I use Gauss's law and when do I use Coulomb's law? First of all, as a fundamental question, what do you think?
You should use Gauss's law anytime you have like a shape symmetry.
Mm-hmm. Yes.
So in this case, you would use Gauss's law since it's cylindrically symmetric.
Yes. And when do I use Coulomb's law? In any other general case, all right? Because Coulomb's law is more general, obviously. Gauss's law can only be used for symmetric, with good symmetries, like a cylindrical symmetry, spherical symmetry, or a totally parallel plate, like we did the parallel plate capacitor, right? You can use something that is infinite long. So for an example, for an infinite long charge, there is a cylindrical symmetry. For an infinite large plate, that has a uniform charge distribution also there. For an infinitely long cylinder that has uniform charge distribution there. For a sphere with uniform charge distribution. These are the what you have been say, 4 categories where you can use Gauss's law. If you go to anything else though, that does not have those kinds of symmetries, then you cannot use it. And then you go to Coulomb's law. But in this case, we can use Gauss's law, right? So what we remember, the Gauss's law starts with the divergence of the electric flux density, which is this one. And you see what I've done here? I said that outside in region 3 is 0. Inside in region 1 is also 0. But, so here, let me in fact, here and here. And here. Yes.
How do you know the inside was 0 for the, may have missed it, but how do you know the inside was 0?
Because there is no charge inside. For this not to be 0, for this not to be 0, it implies that there is a charge somewhere. So inside in region I, region 1, region 3, there are no charges. The only charges exist in region 2. Region 2 is this one. What is it going on? Yeah, tell me. Well, I'm trying to remove this. Yeah, it's region I. Tell me. You wanted to say something. Any questions? So, wherever you don't have charges is this one. Wherever you don't have charges is this one. Wherever there is a charge available is this one. All right? So now what we do is 2 things. We take the Gauss's law, all right, here in region 2. And first of all, so in region 1, we know that there are no charges, and therefore inside this region, what I could do, which I have not done it here, and let me maybe let me do that just to help a little bit. I skipped a step. That's what I did. So add a page. All right. So inside in region 1 is this one. There is okay. Let me see. Okay. This is the first time it's misbehaving. Look at this one. Cut. Okay. I need to be careful. So we take the inside the inner conductor. All right, and from the here, the inside of the inner conductor, and this is region 1. What I do for region 1, this is the center. O. And so let me see, region 1. All right, then what I do here, I take a cylinder in this region that looks like this. and I take it at a distance that I call distance rho, all right? And then I take the divergence theorem, the Gauss's law, which says that the divergence of D in region 1 is 0 because there are no charges in region 1. And then I go on this, on a volume that has this cross-section, all right, this purple cross-section, because I have to apply the divergence theorem, but I need to integrate on a volume. All right, I take this cross-section. And then I take also a given length because that is important. I need a volume. So I take a given length of this cylinder. And then let me call this length L. And then I integrate this divergence in this volume, which is made out of the surface S plus the length. So then I have divergence of D, dV is 0, which from there gives me the closed surface integral of D dot ds. All right? And that is equal to 0. Okay. How have I selected this cylindrical surface with any radius rho? And so what is the closed surface for this cylinder is made out of 3 surfaces. It's made out of this surface S1 that has this normal direction, that has this normal vector as its direction. The other surface here, S2 on the back side, these are 3, it's a 3-dimensional. S2 on the back side, and this is N2, which is along the other direction of N1. And then we have the side. The side surface for this, say, is this one. Now, let's try to find what will be the direction of the electric field. Since this one has a cylindrical symmetry, the electric field in this one, and therefore the electric flux density will be along the rho direction. So the electric field will be like this. All right? And therefore, D, which is, in this case, is free space epsilon naught E, will have only the rho component. All right? So what is the direction of the rho component? It's like this here, perpendicular to the side surface. So from this here, we have that only the side area will contribute, which is going to be from 0 to 2 pi along the perimetry of, in fact, it's going to be just the perimetry, I should say, not, I don't want to do this here. It's going to be the surface area is practically going to be 2 pi rho times L, which is the length, and that's going to be times d sub rho. Because of the cylindrical symmetry, d sub rho is going to be the same everywhere, and that will be 0. So from here, we find that d sub rho equals 0. All right, that's how we find that the field inside the inner conductor is 0. Okay, that's how I got that. So I find for the inside area that di is 0.
That's the divergence.
D
Flux
is
density.
the electric flux density. D is the the divergence is this one. Let me see.
Just get confused.
Divergence is this one of D. But because there are no charges, we also, and because there is a cylindrical symmetry, we also find that the D is 0 by itself. Okay? Do you see that? So somebody can say, well, you tell me that, but I know that I have charges outside. Why these charges do not create an electric field? What then is the explanation? I mean, if you have a charge, creates a field anywhere, any point charge, all right? If I have a point charge here, plus Q, it's going to create an electric field everywhere. So if I have charges there, I have them on this conductor, cylindrical conductor. Why do they not create an electric field inside the conductor?
All the differential charge elements on the surface cancel each other out on the inside.
Yes, because they do create independently, but they eventually cancels out. That's why it's 0. Okay, so that is the explanation. Question?
What was the original question you just asked?
Why is the field 0 inside if the charges, if each of the point charges which are distributed in the conductor, in the green one, since each one of them creates a field, why is the field inside that conductor 0?
Okay, it was because they cancel out since they're
Yes,
a circle.
because they cancel out. Exactly. So that's where I found that D inside is 0, all right? And I have it here. And therefore the electric field is 0. That's where I put this one. And the step is here because I skipped it. I mean, so from this point on, you don't have to rederive it. All right, if you have a cylindrical symmetry and if you have a charge, a void of charge inside, then, and it's cylindrically, symmetrically, it has cylindrical symmetry too, that void, then practically you don't have an electric field there, like it happens in this problem. So you can, if I were to ask you this question, or if I were to give you a problem like that, you can just say it. I would not expect you to prove it. You only have to prove something if I ask you, prove to me that, for example. But if I ask you to make a statement, then I don't want you to prove anything. Now, if you want to prove it because, if you want to do something because you don't remember exactly what happens, that's a different story. But if I were to tell me how much the electric field is in region 1, then just this explanation as we discussed it right now, that the field cancels out from all of the charges around, that's pretty good to me. And so after I do that, I go to region 2. In region 2, I'm working now, all right? You can see here. In region 2, what I did, we have charges. Obviously, they are distributed everywhere in region 2. So what I did is that I took also a cylindrical surface like the other one that I did, like up here. I took something surface like this, but now this cylindrical surface is inside the conductor that has the charge distributed throughout. So now I have a different equation for Gauss's law. And it's different because now I have charges inside the conductor. How did I call this charge? Q. All right, so I will erase this for a moment. Have a charge Q. And I write the Gauss's law. I write Gauss's law like this. And then I take the divergence theorem. So first of all, I integrate over a volume. And this volume is exactly this, how I did this here, all right? But now it has this cross-section, the one that is defined by this red circle, this one. Or in fact, this one, okay? And so now that gives, I apply to this the divergence theorem, which changes the volume integral into a surface integral, exactly like before. And the surface integral is going to have three surfaces, the front, the back, and the side. And from the front and the back is going to cancel, so it's only the side is going to contribute, all right? Exactly the same thing. There is a difference, however, here. The only difference from the previous one is on the right-hand side of the equation. The right-hand side, before it was 0, but now it's not 0 because we have a charge. And when I integrate on the volume, this volume has partly charge, all right, that is very symmetric, cylindrically symmetric. So the charge there is going to be exactly the charge density times the volume that I have now I defined. So this type of a volume, but the charge now is going to be in this ring distributed inside here, that part of the charge, because that's what is enclosed by my surface. So then that charge is P is the is L, the length, times the surface, which is the area from the larger circle minus the area from the smaller circle. You have two circles here, the red one and the green one inside. And the charge that has been enclosed by the volume I consider is only the charge that is in this part here. Only this one. This charge has been considered in this integration. All right, and this charge there, to find the total charge, is this area, the ring. And this area is pi a prime square minus a square. And if I take this area multiplied by the length, I find this volume of this ring over a length L. And that here is going to times the density of the charge is going to give me the total charge. This is the total charge. And then as I did before, this integration here practically gives me that d rho is given by this expression. So it's practically, and here let me put this is square, rho squared minus a squared divided by 2 times qs times 1 over rho. So practically that's what we have. Okay? So I'm going now systematically from one region to the other. Now that I'm done with region 2, I'm going to region 3. And I do exactly the same thing. All right? In region 3, the only difference between region 1 is here. That's 1. The only difference between 1 and 3 is that in 1, when we did the integral over a volume, we did not capture any charge. In this one, in 3, when we, even if there is no charge in this 3 area 3, when we create the volume integral, and this is the front face of this volume, when we do that, we capture charge. And what charge we capture? All of this charge here. This is what we capture. So now, if I follow the previous development, then what I get is this one, that the electric flux density in region 3 is given by this. And it's not 0 because I capture charge. And it gives us this relationship. How would you be able, do you know whether you will be able to derive this expression? Would you like me to derive it for you to see?
Yes.
Okay. So let me do the following. I'll move this here.
Dr. Katehi, could I ask a brief question? It's not necessarily about the content.
Okay.
I have a lecture to run to in 10 minutes. Is it okay if you post the notes on Canvas from this?
Yeah, I
PowerPoint
will
session?
put the
Okay.
notes right now, but I will put the video tomorrow.
Oh, no, that's fine. Just whenever you
Okay.
get to it.
Yeah,
Thank you so much.
sure. Okay. So here, okay. So we'll start. Let me move this down. All of this. Move it down. Okay. So in region 3, we write again the divergence of D is 0 here. All right. In every point in region 3, 0. But the result is going to be different. Exactly because, as I said, when we integrate, and how am I going to integrate here? Let me, in fact, do something to be able to show you. I will take this, make it smaller, and then I will extend this, well, extend this, and I will extend this to see how I'm getting a piece of this. And then also I'm extending this one and this one. Okay, so that's the volume that I have of this. Let me see. And then I also, so this is the physical cylinder. However, when I am defining the area to integrate on, and let me use a different color, so because the ones that I have are very similar. I'll use this one. So this one, do it like this and like this. And now the volume I'm going to use from here is going to be like that inside. I'm going to show it to you like this. Okay. So this is L. And let me erase this one. Okay, so now it's clean. So this is the volume. This is volume V. And when I take this integral and this divergence and I integrate it, I will integrate over this volume V. But this volume V, maybe it's 0 in every place, but is 0 in 3. But this is not 0 in 2, for example. This one equals QS. And in 1 equals 0 again. So when I take this volume that incorporates all of area 2, then practically is going to be the volume integral of this Q sub S dV, and this is the total charge in this area 2, which is, this is area 2. The total charge in area 2, as we said before, is P A, what did we call A prime, all right? Prime square minus A square times L, and all of this times Q sub S. So then this on the left-hand side, that gives me close integral from the divergence theorem, d dot ds. And this is equal to PL A prime square minus A square Q sub S. And then all right, and then this area, the area that encloses the volume, as we said before, is made out of 3 surfaces: the front surface, the back surface, and the side. The front surface and the back surface do not contribute anything because D is along the rho direction. And the front surface and the back surface, the directions of these 2 surfaces is along the Z. So there is not going to be contribution. So D sub S 1, which is the front surface, is going to be along the Z direction, ds1. ds side 2 is going to be along the rho direction. And the back side, ds3, is going to be on the opposite Z direction. So the front 1 and 3 do not contribute because D is along only the rho direction. All right, and it's only the side that contributes. And if we integrate along the side surface is this one. Let me also do this here for you. Let me see there. The side surface is this one. That's the side. That's the only one that contributes to this integral. All right? Because the other 2, the front side, which is like the cross section, the front cross section and the back one, do not contribute because their direction or surfaces are along the Z direction. And D has only one component, which is the rho component. So on this surface, yes.
How'd you know again that it was on the row?
Because of the cylindrical symmetry. We said it's cylindrically symmetric. All right, it's infinite long, has the same distribution of charge everywhere, and therefore it's not going to change. It is not going to have a Z component because there is nothing, it's infinite long. And if there were to be a Z component, it has already been canceled. So it's along the rho direction only. There is no Z component in D. Okay. So here, if we do that, the side surface integral, it gives us, okay, on the side surface 2 of d rho ds, this is going to be 2 pi rho L, which is going to be equal to pi L a prime square minus a square q sub q. Right. Okay, and then practically this is exactly what you got from, so this one, this one and this one goes, this one and this one goes, and I have replaced q, that's why you don't see the q there. It's got d3 rho is going to be a prime square minus a square, and that's 2 rho q. And if you write q from what I gave you, it's 0.5 microcoulombs per meter square. You divide it by 2, gives you 0.25. And that's how you get this expression here. Any questions about this? Okay. Then in the other, so in area 4, it's the conductor, so there is no field inside the conductor, 0. And because the outer side of the conductor has been grounded, that means that there are no charges outside. So also is 0. What would have happened if the outside conductor was not grounded?
There'd be negative charges along the inside.
Yes, you would have negative charges along the inside. And then what happened to region 5? How would you find the field in region 5? How would the charges go? Let's start with that. So that's a separate question. I will move this other part a little lower too. So let's now move it here. And say the following. So a new part of the problem. So it says here, assume that assume at this point that, maybe we'll do it later because it's going to mix up this. Okay, let me bring back the capacitance thing, capacitance question. Okay, so the problem, and then we'll do that other question, we'll do it after the capacitance. Okay, so now let's finish that and then we'll go back. Let me see. Okay. With this now we want to find the capacitance. How are we going to find the capacitance for this? Do you remember how we did it for a regular coaxial? What did we do? Who is going to tell me? Well, how did we find the capacitance of a coaxial?
Didn't you just use that equation over there? C equals 2 pi EL.
Yeah, but how did we find that? Can you just tell me for a moment?
There was some kind of integration.
Yes. What did we do? So we remember that C, so the definition for the capacitance, so I'll write it here. What is the definition for the capacitance? C equals Q over V. What is V? In the coaxial, V is the potential difference between the inner and the outer conductor. All right? So Q is the total charge. And V is potential difference between inner and outer conductor. Okay. Now let's go to our problem. How many conductors do we have here? We have, let me do the cross section again. We have an inside conductor which had also a charge distributed throughout. So let's say the inner conductor was like that, and it was like the charge was distributed here. All right, so that is going to be one problem that we will have to discuss next. So, but let me just do it here so you remember it. And so here we had all of the charge was placed inside this conductor. Okay, and the charge was positive, so it was positive everywhere. I will show it like that. Okay, inside, distributed everywhere. Then we had a dielectric around it. And then we had an outer conductor. So let me make this very thick. So yeah, this is the outer conductor. All right. So to be able to find the capacitance, I need to find a voltage. And the voltage is going to be between the inner conductor and the outer conductor. Now, assuming we have a voltage defined well, assuming that all of the outer conductor is going to be at 1 voltage, and here if it's charged, excuse me, if it's grounded, it's going to be 0. And then all of the inner conductor is going to have another voltage. Now, ideally, when the inner conductor is a perfect conductor, then practically all of the charges is on the surface, all right? We talked about that, okay? In a perfect conductor. So that implies that all of the metal, if all of the perfect conductor is going to have the same potential, and the charges will be on the surface. What happens in practice when your conductor is just a good conductor but not perfect, and when the charges are everywhere inside this? What happens in reality? Do you have the same potential everywhere in this conductor, or there is a small variation of the potential? What do you think?
I think there's going to be a small variation and a little field inside the
Yes,
conductor.
there is going to be a small variation. Why is that? It's going to be a small variation in practice because to move a charge from one position to another inside this conductor, you will need to spend energy. And if you spend energy, that implies that you have to move against, you have to push, you have to put energy in the system to move the charge from one position to another because of all of the other forces that are applied on this by the other charges inside. And if you have to expend energy, that implies that you're going to have a variation of potential from one point inside that blue conductor to the other. But it's going to be small because this conductor is very thin. So even if in practice, a conductor where all of the charges distribute throughout the conductor, it's going to have small variations in the potential. Theoretically, when we solve a problem like that, and in most cases when the potential variations are very small, we assume that all of the blue area will have the same potential. So it's an assumption we make because in reality it's not identical as it happens with perfect conductors, all right? So while in the red is a perfect conductor here, perfect conductor, and because of that, everything is at 0. In the blue, in reality, VD has small variations. However, when we are to calculate a capacitance to get a sense, we will assume, therefore, so we assume here that V sub D in inner conductor is constant. Why do I make that differentiation for you, even if I assume it's constant? So you understand that it is true that if you need to have very good conductors to assume that you have a constant V. That's all, just to bring it to your attention. So now that we have assumed that VD is everywhere the same in the blue area and the red conductor is at 0, how do we find V? We take then the electric field and we integrate it, because what do? We remember that E equals minus divergence of V. And then we are going to identify one point A here and one point B here. And we are going to define this line, which is along the radial direction. And we are going to integrate from A to B of E dot dl along that direction, A and B, which is going to be minus, and if there is going to be only a raw variation, it's going to be minus of well, let me write divergence of V in cylindrical coordinates. And to remember the divergence of D in cylindrical coordinates, I need to get my book. Where's the book? There, because I don't remember that. So the book says at the back of the book says that the gradient in cylindrical coordinates if you wanted to prove it, of course, in cylindrical coordinates, the gradient of V is given as theta V, theta rho along the rho direction plus 1 over rho theta V, theta phi along the phi direction plus theta v theta z along the z direction, a sub z. But here we only have a rho coordinate because of the cylindrical symmetry. So there is no phi variation, there is no z variation. So the only thing that we got is this. And therefore, from A to B, E dot dl gives minus from A to B, theta, theta rho, V d rho, because dl is nothing else, but is A rho d rho. Okay? And so this one is going to give us VA minus VB. And then we have that from A to B E sub rho d rho is going to be minus VA, well, plus VA minus VB. And because E sub rho is constant, well, not from A to B, we found it, that is going to be 1 over rho. So how much we found it? Here, it's 1 over rho. So practically, I'm going to rewrite it here. Okay? And in fact, I will use this one. This is in region 3. So let me use this formula. I will put a constant, though, in terms of the 0.25, a prime square minus a square, and so forth. I will use a constant there. And I will have that E, okay, there. Okay, so this one I need it to go lower, but the other one. So from here, I have that from A to B, this is going to be a constant over rho, d rho, and that's V sub d for our case. Let's assume the voltage d, V sub d. And then this is going to give us the constant. And then we have ln of B, of rho of B, like of B over A equals Vd. And the constant is nothing else but this one divided by epsilon naught, also because D equals epsilon naught E. And so we are going to have A prime square minus A square epsilon naught. Yeah, what else do I have? 0.25 from that micron. And then I have ln of B over A. And what units do I have? Microcoulombs per meter square. And that's going to be the whole thing then, V sub D. This is just the constant. So V sub D will be A prime square minus A square over epsilon naught, and then 0.25. And then you can have, instead of B over A, you can have even B over A prime, but A and A prime are very similar. So it's not going to make you a big difference. if you put either one of the two. And that is your V sub D. And then that's what it gets. You see that I got exactly the same as I did here, where I got already the capacitance. I already used the capacitance. As before, what is this one? Okay, I don't know what this is. Cut. I found what I derived up here, exactly what you have there. And I derived here from Q over C by knowing the capacitance of a coaxial.
How did you get where'd you get the constant over P again?
The constant over P, you mean over rho? This is
Yeah,
rho.
sorry.
Yeah, the constant I got it from, you see, I had to replace E rho. You see that? E rho is nothing else. E sub rho is nothing else but D sub rho divided by epsilon naught in that region here, in this area.
Oh.
Ah, okay. In that area here, which is air, or no, dielectric, excuse me. It should be, it's not epsilon naught, it's air, yeah, epsilon. So because the dielectric is epsilon. Yeah, so it is this one. Okay, there. And D sub rho is this one. We found it in that region. Copy. So if I take this and place it here, so D sub rho is 1 over rho times a constant, where the constant is given here. This one. Is that clear a little bit? Did you see how I got it?
I think so. So E of P was equal to, or E of rho was equal to D of rho over E naught, and then you had that equation from earlier that you plugged into the.
Okay. From before. All right, so practically I called that, I made it equal to 1 over rho times a constant to simplify things that I placed here. Okay, so this one is the same with this one. And is the same with this one. All right. So where? Is that clear?
Yeah.
You just have to follow the solution here to see, to remember how we got that one. You need to remember how we got that one. Okay? Did you follow those derivations then?
So I think all the this was the value for the density, and then they canceled out in every direction. So we did some. We used the Gauss's law to solve for this.
If you follow, you go through, you will see it's all laid out there. You just take this one, this relationship, you need to remember, you need to come and see how we derived it. And then you just place this here. And that's where I got the constant. And you find this. But also, instead of doing the solution from the beginning, what I said in here, or I did a shortcut, practically, or. Instead of doing all of this solution that you see here, I said, okay, I will assume that, as I said, I will assume that V sub D is constant on the inside conductor, the blue. 0 is constant on the outside conductor, which is red. And therefore, we have already calculated this capacitance for the coaxial line. And therefore, what I need to do is to find the voltage in that case, and that's it. In fact, practically, I don't even have to do anything else, all right? I will not have to derive anything. I just said, you know, we have defined since so practically now that because it asks me to find the capacitance. But I can say now that I have already, because it also asks me to find how the fields change, all right? But for the capacitance, I can go and say, now that I have assumed that all of the blue conductor has the same voltage and all of the red conductor is perfect conductor, and then there is a dielectric in between, I know the capacitance from a coaxial line that has a dielectric in between. I don't want to rederive it. The only derivations, the reason we did all of the derivations is because it's asking to find, what does it say here? Find the find the electric field between the two conductors and plot it as a function of the radius. So that's why we did that. And as a matter of fact, if we want to plot it as a function of radius, okay, how are we going to do this? So practically, I'll move this one further down. There. And let's try now with everything that we have to plot D. We have D in region 1. Let me write down what we have. We found from the previous work that D in region 1 is 0. D in region 2 equals here, rho square minus alpha square. It's rho square minus alpha square, 1 over rho, yes, 1 over rho times 0.25, and that was in microcoulombs per meter square, which are the units for this, microcoulombs per meter square. Then in D3 is there a prime square minus a square divided by rho times 0.25 microcoulombs per meter square. And then D4, N is 0, and D5 is 0. That's what now we have found, okay? You followed that, is that right? You followed how do we found those Ds?
don't remember all of it exactly.
But when we were doing that, you followed how we did the derivations.
I think so.
Okay. Now, if we want to plot them, how are we going to plot them? So, in terms of rho, obviously, all right, because that's the only thing that varies. If this is rho, and this is 0, O or 0 is at the center here, all right, at the center. And as we move out, we go through region 1, we go through region 2, so through region 1, then we go through region 2, then we go through region 3, and then 4 and 5. We have everything. So now let's plot. At 0, at rho equals 0, it's 0. And it's 0 until we arrive, is 0 the field until, from 0 until we arrive here, at this point. And at this point, at region 2, it starts getting a volume. Regions 2 starts when rho equals A. So this is going to start going from 0 up and is going to increase until it goes into A prime. Rho becomes equals to A prime, which is, so this is A, this is A prime, this is B, okay? So from from 0 to A, it's 0. From A to A prime, it increases. And it's going to increase, so it's 0 until A, 0. From A to A prime is here, increases like this. And then from A prime in region 3 and above A prime, it goes down as 1 over rho, all right? Because this is a constant here, constant. So it goes as 1 over rho, so it goes down like this. Like this. This goes as 1 over rho. And that's how the field goes. Or d sub rho, about similar. Okay? That is why it is important. However, if you are to find the capacitance, yeah, you can do all of this for the capacitance. And, okay, you can do all of this for the capacitance, but the bottom line is that you can just say that and say, you know, I found, in fact, you don't even need to put this one here. Since we have calculated the capacitance for a coaxial line, and here that is a coaxial, then practically that's what I need to write. Here I just put to find the voltage. All right, that's all to it. And we found exactly the same voltage like up here that I did differently. But that's exactly what it is for the capacitance.
So you can solve it 2 ways
Yes.
for the capacitance? Okay.
Yeah, exactly. So that's, let me move this one. I was not supposed to. I move this down. Okay. I overlapped it. Bad deal. A little, so I need to do this. I'm sorry, let me just move it because students, if I don't do that there, everybody else is going to get confused. So this needs to go a little higher. Okay, any questions about this before I go to something different? I'm not going to ask you anything that long. We're solving problems so you can go through a practice of doing things, but I'm not going to ask you this as your midterm, all right? Is that clear? I'm just using a problem to be able to remind you of a few things that we have done before. Now I'm gonna do some problems that I may ask you, all right? So you can see how they will look, those that I can ask you. Okay. So what I normally do for midterms, and that's why I said, read what I have, what we have discussed. Because what I could do on the basis of what I'm not going to ask you to derive things. So you need to remember that. I'm going to ask you to synthesize things. So let's assume one possibility is to ask you like from what, and then let's see how you're going to do that. Assume that you have a coaxial like this. All right, this is the cross section of the coaxial. And in this coaxial, you have two dielectrics. One here. Okay, let me do it better. Sorry, I can do this better. So one and this, and then have another one. Make it bigger. Make it bigger. And it's this. And style here this. All right. And now we have two dielectrics here. So one dielectric is going to go like that. All right. And the other, so practically I can go and put this one here. So this is one dielectric, and what is out there is another one. Okay. And I may ask you to find the capacitance for this one. How would you do that? On the basis of what you've seen. I don't want you to derive anything. So you can, I want you to use things that you have seen. So who's going to tell me? What did we do for the parallel plate capacitor? What did we do? This is all metal, this one at the center. How did we deal the parallel plate capacitor that had different materials in there? How did we find the total capacitance? All right, so this is a coaxial. This is epsilon 1. This is epsilon 2. Okay, this is conductor. Here, conductor 1. This is conductor 2. How did we find the capacitance of the parallel plate capacitor that had two dielectrics? Remember? How did we do that? So there was one dielectric, another one. Okay, who is going to tell me? Anybody? You guys remember how we did that? We did it this just a few an hour ago. Who's gonna tell me? Anybody? How did we find the capacitance of this one?
We just said it was epsilon naught times the area over the.
No, not for, not for, I don't care at this moment about that. But how did we find the capacitance? We wrote what? Remember? Do you remember that? Does it somebody remember this? Do you remember the problem we solved before? Or you came a little later?
No, I remember.
You like find the capacitance of each
Yes,
plate,
exactly. Yeah,
determine the series of parallel, and
yes,
solve for total.
yes. So we find C1, C1, C2. If this is H1, epsilon 1, H2, epsilon 2. So C1, well, you don't have to derive anything. You will remember, right? It was like A in this area. It was A, epsilon, A, epsilon 1, H1, and C2 was A, epsilon 2, C2, H2, and the total capacitance here, 1 over C total, was 1 over C1 plus 1 over C2. You remember that? Yes? Yes or no?
Yes.
Okay, thank you. Now, what would I do in this situation? There is something similar. How would I get the capacitance of this one? The similarity is the same. It's like one capacitance is here, another capacitance is here. So the inner conductor with the outside dielectric make one capacitance C1, and the other with the other side dielectric make another one C2, where C1 is gonna be like, if this is A and this is A, like A. This is, let me call that A. This is B, and this is C. All right. So this is what we have seen in the parallel plate. Let's put it in a box. So that's we remembered it. So it reminds us something. It reminds us this. Jesus. Okay. It reminds us this. Now, here we'll have the same, because what happens, what is common in this, not the geometry, what is common is the concept that you have, that each of the dielectrics is attached to one of the conductors. So practically, the total capacitance, like here, it's a series capacitance, here is going to be a series capacitance too, and a series combination of capacitances. And where C1, however, while here C1 came out of the parallel plate waveguide, this C1 up here is going to come from the coaxial. And we just found the coaxial. It's 2 pi for this one. So the first one is going to be 2 pi epsilon 1 divided ln of A over, excuse me, C over A. C, B over A. That's for epsilon 1. It's as if you had only, if you had a coaxial that looked exactly like this one here, the inner part only. All right, so like it was like the inner part only. And C2 will be 2 pi epsilon 2 ln of B over C, C over B, excuse me, always. The larger number goes on top. C over B, as if this one was the coaxial, like all of this. And then the total, like I say, this is 1 over C total, will be 1 over C1 plus 1 over C2. Okay, now that's how we would do this. How, if we are doing this coaxial like that, how are we gonna do this one, this coaxial? One here, then we have a bigger one here. There. And the dielectric now goes like this. One dielectric here, there. And that is epsilon 1. And another dielectric epsilon 2. That is A, and that is B. How are we going to find this capacitance? Who is going to tell me? Remembering what we did for this one, the parallel plate. Who is going to tell me? How are we going to do this? Any takers? Do you remember how we did this?
Aren't they in series?
In parallel.
Parallel, yeah.
Yeah, okay. Because they share the same metal. So practically the two capacitances are in parallel. How about this one up here? The two sides share the same metals. Therefore, how are the capacitances going to be? In parallel. C2. Where C1 will be 2 pi epsilon 1 divided by logarithm of B over A. And C2 will be 2 pi epsilon 2 divided by logarithm of B over A. So it's like half of it is one coaxial and the other half is another coaxial, and then you put them in parallel. Do you see how we think for this?
Yes.
Okay.
Do you not have to do anything with the area though, since it's half
What area?
of the capacitor?
So, how did we get? Let me look at the value of the capacitance. 1 second. That's the capacitance is let me see where we have it here. Not the area with the length, but this is capacitance per unit length. Is that what you mean? L?
Yes.
Ah, okay. Yes, for L, if it's not capacitance per unit length, you will have to put an L here, this L. Is that what you mean?
Yes. Thank
Yeah,
you.
yeah, that L, yes. If it's per unit length, you don't place it there. But if it's not per unit length, you put this L, okay? And you will have to put an L here, obviously, but the L is common in all of those. Like you put an area there, you're correct. Like here you put an area, here you put a length. But what I want you to remember is, and then if you put a length, you find the total capacitance. If you don't put a length, each of the C1 and each of the C2 is per unit length. You know, I mean, what it means is that your L is not being a specific length. You call it 1 unit length, for example. All right, do you understand that? So when we say, but what I want you to remember is this for that, and this for this. And then I can put an L here to consider that length. Okay? That's what I want you to remember, that similarity, that if you share the same two conductors, the capacitors are in parallel. But if you don't share the same two conductors, but one conductor is next to one dielectric and the other conductor is next to the other dielectric, that are in series. And then for the capacitors, you use what we calculated before. In the book, for example, for the capacitor, the coaxial capacitor is on page 253, is section 6, 5b. In fact, the book also talks about the spherical capacitor, which we did not do, so I'm not going to cover that. But the book has different practice exercises which point to these two structures. But in any case, only for the book, I have not included the other ones. Only for the book, what I have asked you to read, which is 6.5b, and you're going to find it on the main page, all right, where I show the specific sections that we covered, because the book has a lot more, but we have not covered all of these. For the parallel plate, now, example 612 is exactly the parallel plate capacitor, and with the dielectrics in there. So it's example 612 in the book. And we did it also in my notes. I think that's what we're going to cover for today. Any other questions? So practically, I may give you a problem like this, or a combination, or a problem like this, or I may give you a problem like this. And I think we solved a homework like that too, isn't it? Or something. I remember I gave it to you. This one. Or we talked about it in class, but I do remember that. Any other questions or any concerns?
No, that cleared up my questions.
Okay. I know that is a lot, but what I want you to do is not do all of this. No, I'm not going to ask you to do these calculations. No, I'm going to ask you, however, something like this. Something like this. Now you say, okay, if you're not going to ask me about these derivations, why do I have to do them here? Because I may just ask you to do one minor things, things that we have derived before. I don't want you to re-derive them again. That's all that I'm saying. Since I'm going to show this example that we've done, and everybody else is going to have it, I may ask you something like this, not this extensive. No. It's not going to be that extensive. It's going to be a simplified version of this, a very simplified version. Now, why do we do all of this extensively? Because if you understand how what is important for me is to cover the steps I'm taking, because any example is like this. This is not theory. These are examples we're doing, all right? Theory is to talk about Gauss's law and the divergence theorem, and all of this is theory. But implementation of these to specific structures are example problems, all right? But as I said, I like these short things. I don't like to give you extensive derivations. This is good for homework, not for an exam. An exam that I would like to understand, how do you understand the parallel plate capacitor? How do you understand the coaxial capacitor? How do you understand, what else do we find, like the charge from what is the field? Like if you have, for example, what I may give you is like I have one line like this of a charge, an infinite line charge. We are going to do this example. And another line of this charge. And then I want you to find somewhere in between the electric field. So practically, if you know how to solve this problem, and if you know how to solve this problem, which we have seen, I don't want you to solve them again, then you just superimpose. See, that these are the kinds of things that I may ask you. I'm not going to ask you to rederive stuff. But this problem we're going to do, I may do it on Monday or on Sunday. Any questions? Are you good with this material to go over it? Or is it, you think, too complex and tiresome?
No, I was confused before, but now I understand it. So
Okay, if you know, I know at the beginning, just go through this and then ask me questions if you have. As I said, I'm not going to ask you to derive things, but these last things, to see the relationship or the similarities and to use that will be useful. I would prefer, obviously, to give something on the parallel plate, not on the coaxial, because it's more complex. So on the parallel plate wave, a parallel plate capacitor, make sure you feel very familiar with that.
Okay.
All right, so I'll see you guys on Friday, and girls.
Thank you so much.
All right, take care.
Thank you.
Bye-bye.
Thank you.
Bye.